Alright, welcome back everybody. In this video we start the final unit of AP Calculus AB, Unit 8, Applications of Integration. We're going to start here with section 8.1, finding the average value of a function on an interval. We start with the boxed information here for average value. If a function f is integrable on a closed interval, its average value on that interval is 1 over the quantity b minus a times the integral from a to b of f of x dx. Now, where does this formula come from? And I've always, thought of this and explained this, in the context of an ant farm. Hopefully you all know what an ant farm is. They were very popular when I was a kid. But basically a wooden frame or a metal frame with some plexiglass pieces and then, some dirt in between. So that if I looked at the front of an ant farm, it could kind of look like this. The ants might make a landscape that looks like this. And kind of like I would shake my Etch-a-Sketch, I could shake this ant farm and take all this dirt, and when I shook, maybe the dirt would level out. I think I went a little high there. Maybe the dirt would level out right about there. Okay, that's the average value of the dirt, of the depth of the dirt, right there. Now you'll notice that what we have here is a rectangle of dirt. And this dimension here is b minus a, since it's the distance from a to b. And therefore, the area of this, of the cross-section of this dirt is the average value times the quantity b minus a. Now, of course, how do we get that area? The way we get the area of any region is we take the integral from a to b of the function. And so we end up here. And then dividing both sides by b minus a, or multiplying by the reciprocal, we end up with the formula that you saw above, that average value is equal to 1 over the quantity b minus a times the integral from a to b of the function. That gives us the average value of the function. You can also write this like this, and I frequently do, and I've seen other people do it as well. The integral from a to b of f of x all over b minus a. That's another common way you might see that, but of course that's all algebra. So that's where the average, what the average value formula is and where it comes from. So let's go ahead and we'll look at our first example. Find the average value of the function f of x, which is equal to 4 minus x squared on the interval from 0 to 3. Does f actually take on this value at some point in the given interval? So let's start with finding the average value of f of x from 0 to 3. So the average value is going to be 1 over the quantity b minus a, well, b is 3 and a is 0, times the integral from a to b of the function. Now this is equal to 1/3 times the integral from 0 to 3 of 4 minus x squared. And at this point, this is an integral that I can take by hand, and in this unit we're going to do a lot of taking integrals. Sometimes we'll take them by hand, sometimes we'll take them using our calculator, sometimes I'll specify. If I specify, use the method that I tell you. If I don't specify, then really this is your choice. This is simple enough of an integral that I'm going to go ahead and just take the value of this integral by hand. So I find my antiderivative. It's 4x minus x cubed over 3. Which I'm going to evaluate from 0 to 3. So we got 1/3 times 4 times 3 is 12. 3 cubed over 3, 3 cubed is 27. Over 3 is 9. 4 times 0 is 0. And 0 cubed over 3 is 0. And so doing all the calculations here, that's 1/3 times 3. And so the average value of the function is 1. Is there a value of x where the function actually takes on this value at some point in the interval? Well, if I set 1 equal to f of x here, I can solve this for x. And we get x equals plus or minus the square root of 3. minus the square root of 3 is not in this interval, but plus the square root of 3 is. So does f actually take on? Yes. F takes on this value. And I know where. At x equals square root of 3. Now the second question in this first example was kind of leading us in the direction of where we're what we're going to talk about next, an important piece of calculus theory, which is actually a revised, slightly different form of something that you've already seen way back in Unit 5. So, top of the next page, the mean value theorem for definite integrals. So if f is continuous on the closed interval from a to b, then at some point c in the closed interval from a to b, f of c is equal to 1 over b minus a times the integral from a to b of f of x dx. If you remember back from Unit 5, we had the original mean value theorem, which said that its conclusion was that f prime of c was equal to f of b minus f of a all over b minus a. Well, if we say that capital F is an integral of lowercase f in this formula, then all this mean value theorem for definite integral says is it says capital F prime of c is equal to 1 over b minus a times the integral from a to b of capital F prime of x dx. And then by the fundamental theorem of calculus, the integral of the derivative is, oops, I don't know why I wrote an equal sign there. The integral of that derivative is just the function, which we're going to evaluate here from a to b. And so this right-hand side becomes capital F of b minus capital F of a all over b minus a. And so you see this ties back to our original mean value theorem. It's just the integral of everything in that original mean value theorem. That's our mean value theorem for integrals. All right, example 2. Find the value of c that satisfies the conclusion of the mean value theorem for the function f of x equals x squared plus 2x over the interval 2, 5. So first I'm going to find my average value. So I've got 1 over b minus a times the integral from a to b of f of x. And we're going to set that equal to f of c, and we want to find the value of c. Okay, so first I'm going to go ahead and find the value of this integral. I did the first one by hand. I'm going to go ahead and do this one by calculator. So I've got 1 over 3 times the integral of x squared plus 2x with respect to x from 2 to 5. And that's 20. And so we're looking for when 20 is equal to f of c. Well, f of c, all I need to do is put c into this original function. So 20 is equal to c squared plus 2c. And now I can go ahead and solve this equation however I see fit. I don't think I can factor it, so I'm going to go ahead and solve this using my calculator. So I'll go ahead and graph this function, x squared plus 2x minus 20. And I'm looking for something that satisfies the mean value theorem. Well, the mean value theorem was talking about the interval from 2 to 5. So when I graph this, I'm going to set up my window so that my x goes from 2 to 5. Oops, from 2 to 5, so that I only pick up the solution that I'm looking for. Let's take a look at this graph. Boom, we can see across the axis. I can go ahead and solve. Find that 0. And we get that c is equal to 3.583, with 3.582 also acceptable. I could also have set that up using the quadratic formula to solve for c. Really any valid solution method would be just fine. All right, last example, example 3, comes from free response question number 3 from the 2013 AP Calculus AB exam. We've got a table of values here. It says hot water is dripping through a coffee maker, filling a large cup with coffee. The amount of coffee in the cup at time t equals 0, or at time t from 0 to 6, is the function c, where t is measured in minutes. Selected values are given in the table. Part C, use a midpoint sum with 3 subintervals of equal length indicated by the data in the table to approximate the value of 1/6 integral from 0 to 6. Now remember, the midpoint Riemann sum we're going to use just to find the approximation of the integral. So we want to have this 1/6 constant out in front when we calculate here. And then there's a second part to this question. Using correct units, explain the meaning of 1/6 integral from 0 to 6 of c of t dt in the context of the problem. And we'll do that after we find the midpoint sum. All right, so I'm going to have 1/6 times the midpoint sum. We're using 3 subintervals, so the interval from 0 to 2, 2 units wide, and the value at the midpoint is 5.3. Next interval is 2 units wide. I could factor out the 2 here, but I've already started, so I'm not going to go ahead and do that. And then the last interval from 4 to 6, my height is, it's again 2 units wide, and my height's 13.8. And this was a question number 3 from 2013. This might have been a calculator problem. I forget when they switched over from calculator to non-calculator on question number 3. I forget what year they did that. This might be a calculator problem, but I'm going to do it without anyway. So I've got 25, 30.3, 60.6 is what I get when I multiply everything together in the brackets. And so I end up with 10.1. as my midpoint Riemann sum, and that's actually measured in ounces. The last thing I'm going to do here is explain the meaning of 1/6 integral from 0 to 6 of c of t dt in the context of the problem. So we just learned in this lesson that when I've got 1/b times the integral from a to b of a function, that it's the average value of the function. So this is the average value. And what does the function c represent? Well, it's the number of ounces of coffee in a cup of coffee. So this is the average number of ounces, let's say average amount of coffee. Average amount of coffee in ounces in the coffee cup over the time interval from t equals 0 to t equals 6 minutes. Okay, did I identify everything? I've got the average amount of coffee, I've got what it is, I've got my units in ounces. In the coffee cup over, I've got my time is an interval, and I've got units on my time interval. So I've got everything I want for the explanation of the meaning of this in context. All right, everybody, that brings us to the end of this lesson. There's some practice problems, and undoubtedly, I'm sure there's an assignment for those of you who are in my class. Make sure you check that out. And that's the end of section 8.1. See you next time for section 8.2, where we will talk about connecting position, velocity, and acceleration of functions using integrals. All right, everybody, have a good rest of your day. See you next time. Bye-bye.